Hello everyone, I would like to talk about the field testing applications using MsS system. This is the first module of the field track in our level 1 training course. Before we start, let me say what this track is for and what it is not. It is not a product demonstration. Every photograph we'll see in these 7 modules is a real inspection on a real line, and in most of them, I'll tell you what was found, how it was confirmed, and where the method reached its limit. The limits matter as much as the capabilities. An inspector who knows only what a technique can do will eventually report something it cannot. There is one idea running through the whole series, and I'll state it now so you can watch for it. Everything we produce is either evidence or assertion. The number in a report that the client cannot check is an assertion. The number spotted by the data client can look at is evidence. Our job is to produce the second kind. The first module is the tour. We look at where the guide wave testing is used, and then at the long-term monitoring, which is what happened when you leave the sensor on the pipe. The field track has 7 presentations, and they are in this order for a reason. Field 1, this module covers examples of pipeline inspection and long-term monitoring, where the method is used. Field 2 covers the interaction of guide wave with the defect, and what the technique can and cannot detect. Field 3 covers the effects of geometry features, pipe spot, welded attachments, and clamps, which are what you actually meet on plant piping. Field 4 covers content, coatings, and general corrosion, including wave attenuation and inspection range. That module answers the questions every client asks first. How far can you see? Field 5 covers high-temperature guide wave testings, where the line is running hot and cannot be shut down. Field 6 covers defect size in the report and introduces the MsS sector probe, which is where we use on the large diameter pipes. Field 7 covers applications of sector probe, defect mapping, press vessels, and tank welds. The order runs from what the technique does through and what the limit is to what it has found. If you watch them in sequence, each one uses the one before it. This slide shows examples of pipe inspection applications. Guide wave testing is used on the piping system in oil, gas, and petrochemical facilities, on offshore piping systems and risers, on power generation piping, and on pipeline at the load crossings and levee penetrations. Before we look at the photographs, one sentence about what we are actually doing, because it explains everything that follows. Guide wave testing is not a separate technology from ultrasonic testing. It is ultrasonic testing, so we use the fundamental torsional mode of the pipe T01. And that mode has exactly the same character as a shear wave in bulk material. The particle motion is circumferential, the velocity is the shear wave of steel, and it does not disperse. That matters for 2 reasons that will come up again and again. First, everything we already know from the conventional UT applies here. Signal-to-noise ratio, calibration, the need to demonstrate coupling. Second, because it is a shear wave, leakage cannot spot it, which is why the content of the pipe matters so much less than most people expect, and why water on the outside of the pipe does not matter at all. Guide wave inspector is a UT inspector. The pipe simply guides the wave a long way. This shows field testing using the MsS dry coupling tool. These photographs are from a demonstration at a refinery performed to prove the capability on their own lines. Look at where the tool is installed, between the heat tracer line and the pipe. The insulation and the tracing stayed in place on the insulated line. Stripping insulation is usually the largest single cost of the inspection and often the reason an inspection does not happen at all. With this test, we demonstrated that guide wave testing finds defect in corrosion under insulation. That is the application where this technique earns its place. Because CUI is hidden by definition, you cannot see it and you cannot easily measure it without removing the insulation you are trying to avoid removing. These photographs show guide wave testing in 6 different situations, and I want you to look at what they have in common rather than at how different they are. Top left, a pipeline running through a swamp. Next, a dike wall penetration where the pipe disappears into the structure. Next, a concrete wall penetration. Bottom left, an underwater pipeline tested with a dry coupling tool and an MsS adapter. Then a bridge crossing and the buried pipeline exposed in an excavation. In every one of these, the section that needs inspecting is the section you cannot reach. The pipe inside the dike, inside the wall, under the water, under the road, under the ground. That is exactly the part most likely to be corroding, and exactly the part no conventional method can measure without excavation. Guide wave testing does not inspect from where the damage is. It inspects from where you can stand. You install the probe on the accessible pipe and the wave travels into the inaccessible section and comes back. This is the whole reason this method exists, and it is worth being clear about it before we look at any data. If the pipe were fully accessible, ultrasonic thickness measurement would give you a better answer. And note the underwater photograph. The wave we use is a shear wave, and water cannot support the shear, so water around the pipe takes essentially nothing from the signal. A submerged line is not a difficult case for this technique. This slide shows further MsS guide wave applications: corrosion under insulation, buried pipeline, road crossings, and pipeline at high elevation. High elevation is worth a word. To measure wall thickness at the top of the rack, you need access to the top of the rack, which means scaffolding, a lift, or rope team. To inspect that same run with guide wave testing, you need access to one point on it. The rest is reached by the wave rather than by the inspector. That changes the cost structure of an inspection, and it also changes the safety exposure, because the time spent at height is the time spent installing one probe. These are field photographs of high-temperature pipeline inspection, including a vertical line and lines from 8 MPS up to 20 MPS. One is a 10-inch outer diameter line operating at 337 degrees Celsius, inspected with a dry coupling tool and extra high-temperature ring. The dry coupling tool is what makes this possible. Shear couplant and epoxy bonding both fail above about 230 to 250 degrees. So at this temperature, the dry coupling tool is not a convenience. It is the only method available. There is also a reason these lines have to be inspected hot instead of during a shutdown, and it is not obvious. We'll cover it in Field 5. This slide shows the MsS coupled to pipe surface using epoxy in one case and shear couplant in the other. We have 2 coupling methods, and they are for 2 different jobs. Shear couplant is used for one-time inspection. It goes on quickly. It lets you install the probe around the circumference easily, and it gives excellent coupling for the hours you need it. Epoxy bonding is used when the probe is going to stay. It holds the strip for years. I want to say plainly why we spend so much time on coupling in this training. The waves have to get from the transducer to the pipe wall and back again. And it does that through the coupling. Everything downstream of bad coupling is worthless. The range, the sensitivity, the threshold, the report. No amount of gain fixes it, and no amount of analysis recovers it. This is why the very first module of the equipment track is about coupling, and why I agree that the guide wave report should show the signal that proves that the coupling was good. If the report does not show it, the client has no way to know whether the inspection happened at all. Now, let us talk about long-term monitoring using MsS technology, and this is a genuinely different kind of measurement from everything we have discussed so far. MS technology shoots monitoring because of what stays on the pipe. The iron-covered strip is 4 mm thick, about a tenth of a millimeter, and it is bonded to the pipe surface with epoxy. That is all that stays permanently. The strip is thin enough to live under insulation or under coating, and the epoxy bond holds the coupling for years. Electric wires connect the probe to connection box installed at accessible location, and the coil is not bonded to the pipe at all. Now the important part, and this is a reason monitoring is worth doing. In a single inspection, you compare a signal against the background noise in that record. A defect has to stand above the noise to be called, and we have said that means a signal-to-noise ratio of about 2:1. In monitoring, we compare today's signal against the same probe in the same position measured last year. The pipe feature, the welds, the spot, the corroding all produce the same signal they produced before, and they subtract out. What is left is the change. That means you can detect a growing defect that is far smaller than anything you could call from a single inspection, because you are no longer finding the coherent noise. You are finding only the difference between two measurements. That is the real value of a permanently installed sensor. It is that the same sensor in the same place turns a detection problem into a change detection problem, and the change detection is a much easier problem. This shows an MsS monitoring probe installed on high temperature pipeline at a refinery. Every material in that installation has to be selected for the temperature, the epoxy, the electric wire, and the tape. This is the same principle we will see in Field 5. The transduction is never the limit. The rating of installation is the rating of its lowest rated component, and on the monitoring installation, that component has to survive years of it, not hours. There is also a second consideration on a hot line that is specific to monitoring. The velocity of wave changes with the temperature, because the shear module of the steel falls as the steel gets hotter. So if you measure this line in January and again in July, and the process temperature differs, the signals will shift in apparent distance even though nothing on the pipe has changed. The guide wave inspection and monitoring GWT software measure the difference of velocity and amplitude using reference signals and calibrate their differences before data subtraction for detecting the change. These photographs show two varied pipeline monitoring installation. The top photograph shows an MsS probe installed on a gas pipeline at El Paso, Texas. The bottom photograph shows a 26-inch outer diameter pipeline being prepared for monitoring probe. The upper right photograph shows the monitoring terminal, which is both above ground, so the line can be measured without excavating again. That terminal is at the point of the whole installation. Excavating a varied line costs more than the inspection does, and it has to be repeated every time you want to measurement. Here the excavation happens once. After that, an inspector is connected to a terminal at ground level and take a reading in minutes. Buried lines are also where the monitoring helps most. For the reasons we discussed on the previous slide, attenuation in the buried line is high. So a single inspection has a short range and high threshold, but the comparison between this year and the last year is not limited in the same way because the coherent noise from the soil and the corroding repeats. What changes is the defect. This slide shows the permanently installed monitoring sensor, or MsS PIMS. It consists of the MsS monitoring sensor, the main cable, and the monitoring terminal, and the sensor itself is a MsS coil together with a iron covered strip. The design is built around the three requirements: easy installation, weatherproofing, and long-term coupling. Look carefully at how the coupling is achieved, because it is the part that decides whether the installation is still working for years. Only the iron covered strip is epoxy bonded to the pipe. The coil is fixed in place, but it is not bonded to the steel. That matters because of the thermal expansion. A pipe expands and contracts with the temperature every day and every season for years. Anything rigidly bonded across a large area has to accommodate that movement, and over thousands of cycles, a bond under that kind of strain will eventually fail. By bonding only the thin strip and leaving the coil fixed but separate, the installation has far less exposure to differential expansion, and the coupling stays good far longer. That is what allows the claim of highly reliable data over long periods, and it is why the PIMS is cost-effective for buried, subsea, road crossing, and high elevation pipeline. In each of those, getting a person to the pipe is the expensive part, and this installation removes the need to do it again. This shows a field installation of MsS PIMS on a 12.75-inch outer diameter, 0.7-inch wall, fusion bonded epoxy coated pipeline with the iron covered strip epoxy bonded to the pipe and above ground terminal for access. Note the coatings. This is a FBE coated, and we'll look at FBE lines again in field 4. Because they behave in a way that surprises most inspectors. A bonded epoxy coating is thin and tightly attached, and on such lines we measured a longer inspection range at high frequency than at low frequency, which is the opposite of the usual expectation for a coated buried pipeline. Note also the wall thickness 0.7 inch on 12.75 inch line is a heavy wall. That is a line worth monitoring rather than replacing, and it is the kind of asset where a permanent sensor pays for itself. The application area of guideway testing PIMS are insulated and buried pipeline in refineries, chemical plants, nuclear plants, and electric power plants, high elevation pipeline, high temperature pipelines, cased pipeline at the road crossing, and offshore pipelines. Read that list and you will see the same theme as the very first photographs in this module. Every one of these is a line where sending a person to the pipe is difficult, expensive, and both. Monitoring is what you do when the cost of the visit exceeds the cost of the sensor. Now look at the two installations along the bottom. because the difference between them matters more than it appears. On the left, a single center frequency installation with one main cables. On the right, 3 center frequency installation with 2 main cables. Why would you pay for the second one? Because a single frequency does not find everything. Each center frequency has its own wavelength, and the wavelengths decide which size of defect the wave interacts with strongly. A low frequency has a long wavelength, responds to large general wall loss. A high frequency has a short wavelength and responds to small pitings. It also interacts differently with every spot and clamp on the line. That is the subject of several later modules, and it is one of the things I most want to inspect to take from this training. A single frequency measurement on a pipeline tells you about the defects that frequency happen to be sensitive to. It does not tell you the pipe is clean. When you install a permanent sensor, you are choosing what that line will be able to tell you for the next 10 years. Choose the installation that can operate at more than one frequency. This is the end of the Field 1. In Field 2, we'll look at how the guided wave actually interacts with the defect and what this technique can and cannot detect.